Hi guys, we're gonna do a second question on another mechanics question now on cricket balls being hit around, and this is a question on projectiles, and it goes like this. So we have a ball which is being hit, and the question says a cricket ball is hit from a point of 1.2 meters of height above a horizontal pitch. So this is a horizontal pitch, more or less horizontal, and it is moving with a speed of 16.7 seconds, 16.7 meters per second, and it's an angle of elevation of 35 degrees. Now, by modeling the ball as a particle moving freely under gravity, find part A, the time that elapses before the ball hits the ground. So let's do that part first. Now, from your work with projectiles, you should know hopefully that the handy thing about these questions is that you can calculate the vertical and the horizontal components and accelerations and motions of the things quite independently, so you can split your problem up in components. And here they're asking us for the time of flight, so the time before it hits the ground, so that's going to involve the vertical component. So I'm just going to concentrate on that part of things. And from your work with trigonometry and component splitting, you should know that the vertical component of this vector triangle is this one here, and if this is 16.7 and this is 35 degrees, then the vertical component, or the part of this velocity that's going to be in the vertical direction, is going to be the hypotenuse, which is the whole 16.7 times sine of the angle, which is 35 degrees. So that's how much of this velocity is going upwards, and that's what's going to determine what the time of flight is, how long it stays in the air. So let's first calculate how long it takes this cricket ball to get to the very top, and then we can do the same on its way down, taking into account that there's this 1.2 meters of difference in height. So let us see which equation can we use out of our equations of motion, which are, as I'm sure you know, they are v equals u plus at, and v squared equals u squared plus 2as, and we also have s equals ut plus half at squared, where s is the displacement. So now we have these three, and we want to find the time. We know the initial velocity, which is going to be given by this guy here, and we know the acceleration, which is going to be gravity. In this case, we're going to use minus 9.8 because we are our velocity is in the opposite direction to the acceleration, so we wanted to slow it down. So we want the acceleration opposite symbol, or the opposite sign to the velocity, and so we want to find the time. So then if we want the time of flight, we can just say, okay, final velocity minus the initial velocity divided by acceleration. And the final velocity, since it's coming up and at the top it's going to be completely stationary, then we know the final velocity is 0. So another way of saying that is this is 0 minus the initial velocity, and just to do it with a calculator, well, I'll leave the calculations for later, but v minus u will then be 0 minus that, and that is going to be minus 16.7 sine of the angle, which is 35, divided by the acceleration, which is going to be minus 9.8. So that's minus divided by a minus, so that both will be plus, and that suits us because we should really be getting a positive time when we calculate these things. And so if I do this now on my calculator, it says 16.7 times sine of 35 degrees. We divide that by 9.8 and we get 0.977. So even to 3 significant figures, well, that would be too much anyway for time. So let's round that up, and if it says 0.977, let's say it's 1 second. And let's not get confused. We haven't calculated yet the answer. We just know how long it's going to take to get up to the very top, but we still need to do the second part of the problem to find out how long it takes to hit the floor. So if it takes 1 second to reach the top, let's find out the distance that it travels, because then we can add that to 1.2 meters and we know how high we are, and we can then calculate the time it will take to come down to the floor easily. So let's see, we want to know the displacement that it does, and we've got the final velocity. Yes, we know the initial one, we know the acceleration, so we can use this one here. We can also use this one since we have the t. Actually, yeah, let's use this one, that'll be quicker. So let's find this. S is ut plus half a t squared. T is equal to 1 second, so that S is equal to the initial velocity times the time. And the initial velocity, we had it from before, it was 16.7 sine 35, because we're interested in the vertical only. So that's times 1, so we have 16.7 sine 35 times 1 plus half of g, and g is negative, times the time squared, which is just 1. So therefore our displacement is going to be equal to 16.7 sine 35 minus 1/2 times 9.8. That's 4.6678. So 3 significant figures, that would be 4.68. So that would be here 4.68 meters. So if we add that to the 1.2 that we have initially, that's the amount of distance that we want to cover when we're coming back down. So in other words, 1.2 plus this, so the total height is equal to then 4.68 plus 1.2, so we'll call that 1.2, so that's going to be 5.88 meters or thereabouts. So now we've got for the final part of the question, we've got initial velocity, it's at the very top, so that's 0. Final velocity we don't know. Distance to travel is 5.88. Acceleration is positive 9.8, because now it's going in the same direction as our velocity, so we should see it help it to accelerate. And let me see, and the time is what we're trying to find out. We know it took 1 time for the time up, 1 second for the time up, and now we want the time to come back down. So to calculate that, we need to use, let me see, we don't know the v, we do know the u, and we don't know the a, and we don't know the t, so we can't use this one here. But we know the s, so we can use here the v squared equals u squared plus 2as, and that's why we calculated the s before. So that comes in very handy. So that's our s. So if v squared equals u squared plus 2as, we can calculate the final velocity with this equation, and then once we have the v, we can put it in here to find out the time of flight. So that's going to be equal to our initial velocity, which is 0, plus 2 times gravity times our displacement. So that's just going to be straight 2 times 9.8 times our displacement, which is 5.88, and when you're going to have to square root that, and so our answer is going to be 2 times 9.8 times 5.88. And I know I'm making a rounding error here, but this is just to illustrate the point, so you can do it beautifully and accurately with your decimals when you do it at home. And so the velocity, once we square root, comes out to be 10.7 meters per second. So finally, the last part is going to be to find the time, and that's v equals u plus at that we have to use. So that should be easy enough. If v is equal to u plus at, that means that t is equal to v minus u over a. So now that we know v and we know u that was 0, so we can say that time is going to equal the final velocity, which was final, which is 10.7, minus the initial, which is 0, divided by the acceleration, which is 9.8. Right, and if we take the velocity to be positive because it's going down, and we're taking gravity to be positive because it's also going down, then these two numbers are positive, and our time comes out to be 10.7 divided by 9.8. That's 1.09 seconds. 1.09 seconds. So that's a little bit longer than it took to go up. And if we add them both together, the total time of flight, is going to equal 1 plus 1.09, will be 2.09 seconds. On the back of the book, if you've got this exercise book, you might see that the answer is a little bit different. That will be because of the rounding that I've done here. But you get the idea. You get the time to go up and the time to go down, and you add them, and that's one way to solve the problem. There is a quicker way, but we'll leave that for another time. And this is good practice anyway, splitting up the problem in several parts and using our equations of motion to find our answer. Alright, so thanks for listening, and I'll see you in the next video.